everybody. Welcome to this week's DeFord lecture. We're very happy today to have Barbara Carrapa from the University of Arizona joining us. And Brian Horton's going to tell us a little bit about Barbara in just a second. Just a quick reminder, I expect everybody here next Thursday, right?
Thanksgiving.
Okay, no, actually next week is Thanksgiving, so obviously there's no DeFord next week. The week after, however, want to make sure that everybody has on your calendar that we have two events. Tuesday, we have our graduating master's students presenting the results of their research. So please come out and support our master's students for their master's presentations. And then on Thursday, Isaiah Bolton from Georgia Tech is going to be presenting. So that's the week after Thanksgiving. But this week, we're very happy to have Barbara Carrapa from the University of Arizona, and Brian's going to tell us what she's going to tell us about.
All right. Thanks, everyone. It's a real pleasure and honor to introduce Barbara Carrapa. She's a professor and the head of the Department of Geosciences at the University of Arizona. She obtained her degrees at the University of Pavia, which, as you know, is in Italy. And she then received her PhD at Vrij University in Amsterdam, and then did postdoctoral work at the University of Potsdam in Germany, and then has had faculty appointments at the University of Wyoming and now the University of Arizona. Her expertise is in sedimentary geology, tectonics, climate, and thermochronology, and the interactions and intersections amongst those topics. She's best known for studying the evolution of major mountain belts from the sedimentary record, namely the Andes, the Himalayas, the Pamirs, the Alps, the North American Cordillera, really a global perspective on this topic. She's also well known for doing detrital thermochronology. So she's using not bedrock, a combination of bedrock and detrital minerals for thermochronological studies. So a lot of this effort has focused on the interplay or interactions, the synergy amongst some of these different topics: tectonics, climate, and mountain building and basin evolution. She's recently received the Dickinson Medal, which honors mid-career scientists, let me quote it here, who has significantly influenced the sedimentary geology community with innovative work, with a track record of impactful publications, pioneering approaches, and the establishment of an influential research program. So today she's going to give us a talk at what appears to be a very, very regional or global scale, rising from the ashes, marine and continental feedback responses to Andean volcanism and Miocene climate. Take it away, Barbara.
Thank you, Brian. Well, I'm very excited to be here today. I just had a fantastic, day speaking with a lot of you about science, and that's been really, really nice. So what I'm going to talk about today is something that is a little out there for me. Is not actually my specialty, but is a classic example of curiosity-driven science. So it's not funded, it's not published yet, and it's the result of just me and one of my long-term colleagues, Mark Clements at the University of Wyoming, who is a paleontologist, paleoecologist, working together in the Andes for many years, looking at the response of mostly continental systems and sedimentary basins to climate and tectonics. And that kind of led to us having a lot of kind of crazy conversations over wine and campfire while we were doing fieldwork in the Andes and come up with this idea. So today I'm going to actually look at the potential effect of volcanoes and volcanic activity in the Andes on global climate, specifically in the late Miocene. And so why the late Miocene? Well, the late Miocene is actually a really interesting time in geological history. It's warmer than today, but as PCO2-like modern, so has been considered by many sort of kind of an analog for what we're looking at in the future. There are also very interesting shifts in the Miocene, specifically the late Miocene cooling that we're going to focus on, which is actually a synchronous shift or a change in sea surface temperature that has been seen or observed from the marine record in both hemispheres, with ocean temperatures dropping to near modern, between about 7 to 5 million years ago. And also, at the same time, we're actually seeing some significant biogeochemical shifts, like the late Miocene carbon isotopic shift, which I'm going to talk about, and the late Miocene biogenic bloom. So this is all happening at the same time. And again, I was working in the Andes for a lot. I've been working in the Andes for like over 20 years, doing a lot of field work, mostly tectonics, right? Not so much paleo and paleoclimate and paleoecology. But this is, as I said, is the result of interactions with colleagues doing different things and kind of bringing together different fields. This is a recent paper that we published in 2019, where we basically saw that in the late Miocene, the climate is responsible for systematic shifts, for example, in the stabilized geochemistry of carbonate nodules in a lot of the basins in the central Andes, which we associated with global climate change. And also those shifts corresponds to significant changes in ecosystem responses, like for example, changes of plants from C3 to C4, and also in the increase in the proportion of mammals with eye crown teeth, like hypsodont, like this guy here, the armadillo, which is still around today and was around in the Miocene, Pliocene. So this kind of research led us then to think about more broadly about, okay, if this late Miocene climate shift is global, what are the responses of maybe the marine, environment and marine ecosystem? And then the question is, what is driving it? And that's where when we came up with this idea or hypothesis that I'm going to present today. So another piece of interesting information that led us to this research is that the observation that there's this place called Cerro Ballena in Chile, in Bahia Iglesias, we're about 4 hours north of Santiago de Chile, where people have observed this mass stranding in the late Miocene. So there's like this, very wealth of fossils in these layers that they're 5 to 11 million years old, where you have these whales that all seem to have died kind of pretty rapidly during that time. Now the question about why these whales died at that time and what the cause for that mass stranding is still kind of unresolved, although there are some ideas out there. One of them is that this mass stranding is associated with algal blooms and volcanism. So the idea is that increased volcanism has basically fertilized the ocean, increased productivity, led to algal blooms, which in turn can actually have a lot of toxin and harmful substances to the ecosystem and to vertebrates. So they died off because of that, either by eating algae or by actually breeding ash flow at the time when they were alive. So that's kind of an open question, and we're going to actually go to Cerro Ballena in a couple of weeks to try to constrain more the stratigraphy, sedimentology, and figure out answer that question. But also, this has led also to me looking into the volcanic record and really thinking more about how volcanism might have played a role in late Miocene cooling and overall in ecosystem responses in the marine record. So this is a map of a DEM of the Andes. Those dots represent geochron ages, so the crystallization ages of volcanic rocks preserved today in the Andes. And I just want to show you, well, the Andes, and I'll get into the tectonics in a minute, it's an active system that has had a volcanic arc active for a long time. But if we actually look at, let's say, the Cenozoic record of magmatism from the geochronology, you can see that there is definitely a spike in volcanic activity at about 7 MA. And that, the proportion of let's say, late Miocene ages, if you look at even back into the Mesozoic, is much, much higher than any other ages that you find preserved today. So that is kind of intriguing, right? Because that's right on, it coincides with the late Miocene cooling. And that's also the time where you have this APVC magmatic activity, which stands for Ultiplano Puna magmatic complex, which is a major, massive volcanic complex active in the Miocene, Pliocene in the Andes. So there is definitely a significant increase in volcanism in the Neogene. So the idea that that might have affected primary productivity in the ocean and potentially control marine ecosystem, it's viable. So this is the Ultiplano Puna volcanic complex. As I said, is this big, is one of the largest and youngest volcanic fields on Earth. It spans for about 20 degrees south, goes all the way down to actually, this is sort of the concentration of magmatism, but it goes down all the way to 25. It's about 200 kilometers in diameter and there is this 11 kilometer thick low velocity zone, which has been interpreted to as a plutonic complex that sourced the APVC. So actually geophysical studies show that the amount of material that fed this volcano or this volcanic center is much larger than if you just look at the surface geology. So now the outstanding question that I want to tackle with this talk is what controls late Miocene cooling within the longer Cenozoic cooling trend. And so this is the delta 18 curve from the marine record over time. I'm sure you're familiar with this, that has been used, is used as a proxy for temperature over geological time. And you can see that the late Miocene is actually, let's see if this is going to work, yeah. It's actually pretty short, right? But it is a very significant drop in temperature that we observed, and within a general cooling trend within the Cenozoic. We also, in the Miocene, we also see periods that are much warmer, like the mid-Miocene climatic optimum, which is another question and another problem. So we're just going to focus for now at the time between about 7 to 5 MA. So let's look at some ideas about models for driving global cooling in the Cenozoic. One of the classic one is chemical weathering. The original work and the original ideas about chemical weathering suggested that the Himalayas were the culprit for the Cenozoic cooling that we observed from the delta 018 curve. More recent work suggested is actually weathering of calcium and magnesium rich mafic and ultramafic rocks within the tropics that does a lot of the work in terms of drawing down CO2. And then another recent idea, again suggesting that tectonics is playing a major role, is that changes in seafloor spreading and slowing down of seafloor spreading in the Cenozoic might have actually reduced CO2 outgassing, contributing to a reduction of temperatures over the Cenozoic, and that's Herbert et al. 2021. Okay, so those are the two of the many models out there, but two of the most, let's say, popular ideas. Now, when we're looking at volcanoes and the carbon cycles in general and global climate on long time scales, CO2 is added to the atmosphere by volcanic degassing. So when we're talking about volcanoes, most people think about volcanoes are actually not helping in drawing down CO2, but it is actually pumping CO2 in the atmosphere, which is correct. So it's added to the atmosphere by volcanic degassing, metamorphic decarbonation and oxidation of organic matter, and is removed from the system by chemical weathering, which delivers alkalinity to the ocean and sequesters carbon via the precipitation of carbonate rocks. So that's those are the two main ways you get you control the global carbon cycle. So the common thinking is that CO2 outgassing contributes to warming or over geological time, not cooling. And that's actually, this is one of the many papers that shows that. Actually, I think, Brian, you're an author on that one. But there is also another piece of the puzzle that is not considered here when thinking about volcanism, is that volcanoes and volcanic ash can fertilize ocean water, and that can initiate cooling through increase of the biological pump, right? That can draw down CO2. And that has been suggested as a way to initiate, for example, significant cooling in geological past and even glaciations, right, throughout geological time and in deep time. So here are the hypotheses that I'm going to try to test today, is that enhancing of the biological pump and CO2 drawdown, that the Andes are responsible for that through increase of volcanic activity. And so that fertilization of ocean water through iron and, for example, silica from volcanoes has affected diversification and abundance of primary producers and also consumers like whales within marine communities. So if that's correct, what we should expect to see is a systematic correlation among a lot of different things like volcanism, primary production, marine consumer diversity, sea surface temperature, and PCO2. And the null hypothesis will be that you will not have a systematic correlation. So today, all I'm going to show you is correlation, and probably the question you'll have is like, well, that's just correlation, not causation. We'll get to that after. But I will argue that because we see systematic correlation of all these things together, that there is a pretty good chance that that hypothesis is correct. So we're going to look at the Andes as a natural laboratory because it is the site of the longest continental volcanic arc on Earth. Active volcanoes in the Miocene were in the easterly belt, so you have actually a way to get that volcanic ash into a key place, which is the equatorial Pacific, in the right time. So you can fertilize the equatorial Pacific, which is one of the most productive areas and really controls global climate. The product of silicate weathering was also delivered through the Amazon to the Atlantic, and the Amazon River, the drainage that we see today was started at about 9 MA. And then you have the Humboldt Current, which at least since the mid-Miocene provided upwelling and nutrients to the west coast of South America. So you sort of have the perfect recipe for all these things to really work together to affect potentially the biological pump and global cooling. So the Andes are also the largest contributor of silica to the world's ocean. So this is a figure showing particulate silicate yield versus dissolved silica, and you can see that the Andes are way up there. That was surprising to me when I actually looked at that. So they're actually the major contributor of silica to the ocean. And silica is a very important, factor in ocean fertilization and the biological pump. So how do volcanoes actually affect the biological pump? Well, you have nutrients like phosphate, silica, iron, and manganese that can actually fertilize the ocean either by wind or rivers. And the low pH of volcanic ashes enhances the solution of iron-bearing silicate minerals, which contribute to ash fertilization and enhances the biological pump. And that's just an observation from modern volcanic eruption and the productivity, right, around volcanoes that produce ashes that they have low pH. And then the reaction of surface water with newly erupted volcanic ash can lead to the production of micronutrients and trace metals, which enhances the primary production and the biological pump. So a lot of studies have shown that that's the case, that you actually can have a lot of fertilization and increase in primary production. The question is, how much of that do you need to really kind of draw down CO2 and affect the global climate? So now we're going to look at some diversity plots and how all these little creatures in the ocean responded to late Miocene cooling. So this is just different figures showing Cenozoic global plankton diversity, and it's you have calcareous nanofossils, diatoms, planktonic forms, and radiolarians. And of all of them, I would say that all but the nanofossils are actually responding. You see a pretty high spike or increase in diversity in the late Miocene, particularly when you're looking at the diatoms. So the diatoms are clearly showing an increase in abundance and diversity, in the Late Miocene. So again, to go back to silica and the silica flux and ocean fertilization, dissolved silica controls productivity, and diatoms make up 75% of primary production in coastal areas, and also form the basis of marine food webs. So if you affect diatom production, you're going to affect, the evolution of like, for example, marine mammals and the whole food web and ecosystem. And studies have shown that algal blooms can sequester enough CO2, again, as I said, to trigger glaciations in the geological past. Again, that's an interpretation, but those are things that those are ideas that have been out there now for a while. So just a little bit more about diatoms and the carbon cycle. So diatoms use silica to build their structure through photosynthesis, and they consume CO2. And when they die, they serve as a carbon sink. So that's what goes into the POC, which is the particulate organic carbon. So increased delivery of organic matter to the deep sea will result in a drop in bottom water dissolved inorganic carbon, DIC, and delta 13 C values as carbon is remobilized by consumers. So this is important to keep in mind, because I'm going to show you next some plots showing delta C13 values and the carbon shift in the Late Miocene, and that might be actually related to increase in productivity in diatoms. Now this is where the whales come in, and again, that's mostly Mark's story, but I love whales, so don't know anything about that, but I'm happy to go along with this because I think it's a really cool idea. The connection between diatoms and whales have been shown before, so that's not new. Studies have shown that the whale diversity parallels the diversity of diatoms and changes in ocean temperature. So there is this, global, seems to be like a global connection between diatoms, whales, and global climate. So now the question is, how can we put all the pieces together, and how much does that matter, right, when it comes down to CO2 drawdown and global cooling? So now I'm going to jump back into tectonics and geology of the Andes before I get into more of the different data sets. So the Andes, this is just a very simplified cross-section of the Andes, are formed along a converging margin as a result of subduction of the Nazca Plate under continental South America. As I said, there is a volcanic arc that has been active since the Mesozoic, and is active today. So there's definitely a lot of magmatic activity that has played a role in the geology of the Andes and in deep time. Now the question is, can we tease out times that when magmatism was more was intense in the geological record? So this is again a plot that shows the frequency of Andean volcanism from uranium lab geochronology data from zircons from magmatic rocks present today at the surface. And you can see that if you just concentrate, and now I'm going to just concentrate on the last 20 million years because that's what I'm interested in for this talk. And if you just pull out the last 20 million year record, you can see that you have this big spike at about 7 MA, which is the Late Miocene. And you have interval of significant volcanic activity from 9 to 3, and you can tease out some smaller peaks, but the bottom line is that at 7 MA you have a really a significant increase in magmatism. Now you may ask, well, this is just maybe biased because you're just looking at volcanic rocks preserved today at the surface. We see the same, and I don't have actually the data pulled together, but I'll have to eventually put that into the paper. We see the same, increasing frequency of volcanism from the sedimentary record. I mean, the number of ashes in the Late Miocene is much higher than any other time in the Cenozoic. In fact, if you go back into the early Miocene, the early Cenozoic, you don't have a lot of ashes preserved in the foreland basin. Now, this is for the thermochron people in the room, or tectonics, thermochron, erosion aficionados. This is a compilation of all thermochron ages that we have from the Andes right now, and it's a combination of both fission track data and uranium-thorium helium. And in general, you know, you can see that the blue colors are younger ages, and the kind of the whitish, brown, orange colors are older ages. And you can see that for the, at least for the central Andes, where, you know, you have maximum thickness and maximum width of the orogenic belt and maximum shortening, erosion is concentrated on the east, okay? And that's a function of the fact that the deformation has propagated from west to east through time, was in the Eastern Cordillera by, let's say, Miocene time, and then you're in the easterly belt, so that's where you get all the precipitation, right? And erosion is concentrated right there. Once you get into the plateau region, it's dry, and not much erosion has happened there for quite a long time. Now, we have data, at least for part of the plateau, at least the Puna Plateau in northwest Argentina, that suggests that you have high elevation that were established by 35 MA, so really early on. And also aridity was established pretty early on in that part of the Andes. So you have a lot of material coming off of the eastern part of the Andes that can get, that was actually available to be delivered to the Atlantic by the Amazon by 9 MA. So now if you look at the climate setting today, you see that the central Andes and northern Andes are in the easterly belt, so the precipitation is coming from the east, and so you have an orographic barrier to the east of the orogenic front, whereas as you go south of 30 degrees south, most of the precipitation is coming from the west and is concentrated on the west side. Now, this configuration has been in place for a long time. So, you know, at 9 MA or for late Miocene is safe to assume that that's kind of the same situation we're looking at that time. Okay. Now, because also the Andes are so long, and because of their location, they are 8,000 kilometers long, and they're so high, they actually have controlled global ocean and atmospheric circulation through geological time. So that's, you know, they're a significant player when it comes to global climate. In terms of aridity, you know, places like the Atacama Desert and the Puna Ultiplano Plateau were high and dry, I would say by 20 MA, give or take. By 9 for sure. So again, by late Miocene, you know, that's the time that we're looking at. They were high, that region was high and dry. It was, sustained aridity was established by 6 MA. So you have basically places that can deliver a lot of dust to the ocean as well, not just ashes, but you can have a lot of dust going into the equatorial Pacific through the easterly. And then, as I said, the Amazon River was established by at least 12 MA. By 9, you have an increase in input from the Amazon into the Atlantic Ocean. And so you have, again, all this material coming off the continent going into the ocean. Okay? The Amazon is the largest river in terms of discharge in the world, so there's a lot of silica and other nutrients coming in from its drainage system. And the discharge of the Amazon represent about 20% of the worldwide river in water flux to the ocean. So it's you know, safe. It makes sense to think that the Amazon was probably playing a key role as well in global climate and ocean fertilization. However, we're going to focus mostly on the Pacific side and the equatorial Pacific. And then the Humboldt Current brings cold water from the Southern Ocean to the equatorial Pacific. It dries up whaling and brings nutrients to the west coast of South America, and it was established since the mid-late Miocene. So you have the right setting to get a lot of stuff into the equatorial Pacific and the Atlantic by late Miocene. You have the Humboldt Current that provides mixing and a lot of nutrients, so you have all the right ingredients for increasing productivity. Okay, now we're going to get into a lot of plots that are a little complicated, but hopefully I'll spend enough time where you can focus on the right shifts here. So this is again, those are the magmatic ages on top. The dark blue is the big spike at about 7 MA. The lighter blue is just when there's an increase in magmatic ages within the Miocene. Now you come down, this plot shows the delta C13 values from the ocean. Those bars are basically indicating different places where you have opal deposition and the shifts in opal accumulation through time. And this one is the delta 18 carbonate values that is used, right, to infer global climate in the past. So the Andean, if you actually look at Andean volcanisms and you look at when that happened, the increase in Andean volcanism, that coincides with the late Miocene biogenic bloom, or late LMBB, and that is this bar here, which is highlighted in pink. Okay. The late Miocene biogenic bloom is characterized by high accumulation rates of opal from diatoms and calcite from calcareous nanofossils and planktonic forms. And so it's kind of interesting that, and people have interpreted that as potentially being associated with climate and a variety of other things. And you also see, here in the Miocene, you see a shift between opal deposition moves from the equatorial Pacific to the eastern equatorial Pacific at that time. Okay, so you're kind of we're in the right place in terms of where we see major productivity kicking up, because obviously those are global curves. So the initiation of and the establishment of high opal accumulation rates in the eastern equatorial Pacific at about 8 MA support volcanic input as the culprit for this increase in productivity. So supports the idea that the Andes are playing a big role in that. Now, that spike in volcanic activity also coincides with the late Miocene carbon isotopic shift, which is highlighted here with the pink box, and that corresponds to 1 per mil drop in benthic marine delta C13 values, which may reflect an increase in productivity that will also enhance the biological pump. So again, there's different explanation for that, but that's one of the major one. That drop is actually related to increased productivity. So what are the evidence of increased productivity, especially in the equatorial Pacific? So we're actually looking at, well, those curves actually represent productivity for all these different sites, but in particular site 846, right, is in the equatorial Pacific just west of the northern central Andes. So that's a kind of a key site for us. And they all show, for all sites from the Pacific Ocean, you can see that there is an increase in productivity at the right time, which is actually, interesting for us. Again, in terms of the blue and the dark blue is where you have the spike in volcanic activity in the Andes at about 7 MA. The lighter blue is the overall, Miocene volcanic activity that is still higher than the background Cenozoic one. And then the light purple bar here is actually when you have a global decline in productivity. So this is another set of plots that actually shows organic carbon accumulation data from the equatorial Pacific. The gray bars are basically the organic carbon values for today. And so anything above it suggests that you're way above modern values. Okay, so if you're looking at just 846, which is a site in the equatorial Pacific just off the Andes, you see that you're way above modern values for the late Miocene, Pliocene. So you're not only seeing increased productivity, you're also seeing a lot of increase in organic carbon accumulation, right? Which means that you have a record of taking that carbon and depositing it into the bottom of the ocean, which you need to do, right, in order to store carbon. Now we're going to look at global sea surface temperature, so SST, sea surface temperature, and PCO2. Now the values of PCO2 are a little more kind of questionable also because these PCO2 values come from boron isotopes. That's a proxy for PCO2. It's not straightforward. There are people in this room that know more than I'm sure I do that about boron, but I've read quite a bit and it's like not, straightforward. But let's look first at the sea surface temperature. You see a major drop in sea surface temperatures globally in the late Miocene. Now, for the PCO2 values, you do see a little bit of a drop at about 6 MA, right? So, they kind of go together, but it's not a clear, match. But I will say that those are probably the best model, or let's see, values from proxy data that we have so far. This is a recent paper just came out in 2022. So how are the marine mammals doing? If the diatoms are kicking up and then they're increasing in production, then and marine mammals like whales are eating off of diatoms, then you should expect to. And if that relationship between diatoms and whales that has been suggested before it's valid, then we should expect to see a similar response. So again, that the darker blue line is when you have the spiking magmatism from the Andes. This curve is basically, these different curves are showing increased diversity of diatoms, and those are basically curves for diversity of different mammals, marine mammals, through time. And this one is actually a curve that shows extinction rate for the same mammals. So you seem to have definitely increased diatom productivity. You have a response of the marine ecosystem in the Miocene, but also decline and an increase in extinction rate, which is kind of interesting, right? So it seems like first they kind of respond positively, and then there is also an extinction happening. So the question is, how are these related, and why is that? The current thinking is that this extinction event at about 7 MA is associated to global cooling and fluctuating seas, so changes in relative sea level that are basically removing the habitat that they like to hang around in. So, and that will affect basically evolution and lead to extinction. So now this is just like, you might ask, well, okay, I show a bunch of wiggle plots and, yeah, they correlate sort of, in terms of time, but can we do better than just looking at correlation of different populations of data sets? So this is a multidimensional scaling analysis and which measures similarity between different data sets. Is usually used for geochronological data, so the people who are doing geochron and DZ, they probably are very familiar with this. I'm actually using this the same way, but instead of just using ages, right? I have ages, those are volcanic ages from the Andes. I also have whales and different kinds of cetacea, sirenia, pinniped, and diatoms, right? To just look at basically how those different populations correlate. Now, the correlation diatoms, cetacea has been shown, not by me, by other people. So here, and I should say that the darker line is a first degree, the nearest basically neighborhood and the closest degree of correlation, whereas the dashed line is the second degree of correlation, right? So if the diatoms whales correlation is correct and has been shown in the literature, and this is their level of correlation when you're actually looking at the data, then I will argue that correlation ages whales and ages diatoms also works, because it's kind of basically the same distance, So, I mean, this plot basically suggests that statistically those different populations of data are correlated. And they're not just like, it's not just a random, connection between them. Okay, so then another important thing about whales and how they play into the overall carbon cycle, right? Now that we maybe believe that they are part of the overall budget and they're connected to diatoms and volcanism, at least for the equatorial Pacific, is that whales are important kind of also agent in mixing water and nutrients in the ocean. They feed on krill, which feed on diatoms, and they recycle iron in surface water. So they just get that iron and nutrient going, right? And then when they poop, the whale poop is concentrated in iron, about 10 million times as much iron as Antarctic seawater, which in turn enhances diatom production. So there is this kind of feedback relationship between diatoms and whales. And then when they die, they serve as an important carbon sink. And there has been a lot of actually studies, which I did not know, looking at how much carbon they can take down when they die, and it's impressive. So there are studies that I actually think I have next showing that this is just came out recently in 2021, showing that whales play a key role in carbon cycling by consuming a lot of biomass, and pre-whaling populations consumed about 430 million tons of Antarctic krill and sank up to 1.9 million ton of carbon per year to the bottom of the ocean. That's huge. So then the question is, okay, if we use those kind of values and just propagate them into the geological past, how much of that is going to affect the global carbon cycle? And that's the next step in our study. We don't know yet. But the bottom line is that they're a very important player in the global carbon cycle. So to summarize, we kind of are looking at a perfect storm where you have intense volcanism in the late Miocene, mostly associated with the APVC, the Ultiplano Puna volcanic complex, in the central Andes, which also correlates with the late Miocene carbon isotopic shift and the late Miocene biogenic bloom. And the idea is that nutrients from the volcanoes from the Andes were transported to the Pacific Ocean via the easterly, so wind, and to the Atlantic via the Amazon River. And these nutrients were able to fertilize the ocean and enhance the biological pump and primary production, affecting whale evolution. And then whales and the Humboldt Current contributed to nutrient recycling. And then diatoms and whales together contributed to carbon sink, leading to late Miocene cooling, or at least contributing significantly to late Miocene cooling. So now the next step that we're going to try to do is to quantify all this, because obviously this is an idea, but the question that remains is like how much fertilization do you need? How much do you have to crank up the silica, little knob and the iron knob to fertilize the ocean enough to get the biological pump to actually draw down enough CO2 to cool the climate, right? And that's going to happen in collaboration with our colleague Pietro Venezio, who was actually here until not long ago, is going to use Earth system model to basically get all the pieces into that model and really look at the effect of increased silica and iron in the equatorial Pacific from Andean volcanoes to see how much of that affects global carbon cycle and ultimately climate. Okay, so to conclude, and I already kind of said that, but we think that mountain building and tectonics, specifically from the Andes and volcanism, together with dry paleo-environmental conditions in large parts of the Andes, and especially the central Andes, increase the ocean biologic productivity through ash-rich, wind-blown, and river inputs into the ocean, both the Pacific and the Atlantic. And then diatom blooms affected marine ecosystem and together contributed to organic carbon burial, atmospheric CO2 drawdown, and global cooling, at least since the Neogene. Now, the interesting thing is that the Andes have been active throughout the Cenozoic, and so it's possible that Andean volcanism has affected the overall, Cenozoic climate on larger timescales, but that will have to be tested because, of course, you all know that the Cenozoic is not just a simple cooling trend. You have warming trends as well. So how that works, we don't know. But that's kind of the idea, at least for the Neogene, for the Late Miocene, cooling, and and we're keeping, this research has just kind of started. So hopefully there's going to be more coming out. So stay tuned. Thank you.
Okay, questions?
Could you talk more about the whales? It's kind of shocking that this. It doesn't seem like there's enough whales.
Yeah, not.
Do we have enough whales to influence climate?
Yeah, the question is, it's a good question, and I don't know the answer to that. Back in the Late Miocene, how many whales we had? Sorry, just took it off in my. Oh, be back. Okay. So I don't know the answer to that. We'll have to really kind of see how much the whales are actually affecting that. What I can say is that the diatoms, I think, are definitely, affecting the global carbon cycle, and they're affecting whale evolution. How much the whale are playing a role in the global carbon budget is to be, constrained. And I think the models, unfortunately, right now cannot get the whales in the model. We'll try to see if there is a way to put the whales in the model. Right now, it's just primary producers that you can put in. So we'll see. But yeah, we'll try to figure that out.
Danny?
So, very intriguing, but my first question is are there other culprits, right? We've seen this Late Miocene cooling for some time, and so, are there other global alternatives? Then I guess my other question was going to be it would be pretty easy to look offshore to IODP records, but there are no IODP records in the South Pacific, really. So, where are we going to go next? Because you would certainly want to see are there more ashes? What's the sediment chemistry in the South Pacific in terms of production? Because you're going up offshore Ecuador, and that's pretty far away.
Yeah. Yes.
So there's sort of two questions.
Yes. So the first one is yes, there are other. I'm not arguing that that's the only one at all. I'm arguing that is a significant player that has not been accounted for. Other players are, classic, right? Increased chemical weathering from the Himalayas. Sure, we're all working on Miocene is active. Monsoon, so a bunch of stuff getting into the fans. Yes, that's probably playing a big role too. CO2 decrease from mid-ocean ridges is slowing down. Sure, for the Cenozoic, the record is pretty sparse. You can't go down to the detail of the Late Miocene necessarily, but that's probably also playing a role. So I will argue that all of that plays a role, and so it's the question is how much of these is actually affecting the global carbon cycle at all, if it's actually significant or if it's not. So I think it's more in the context of when you put all the pieces together, how much of that is that 20% of the global or not? That would be pretty cool if it were 20%. I'm not arguing that is the only one driver. In terms of ODP record, you're right. There's not much, and we're trying to find as much as we can in the right places. And that's the next step, is to collect all the possible data. A lot of the data that exists is out there in terms of productivity, but there is not much more. So yeah, ideally we'll get more sites from from the Southern Ocean, but that go down deeper to that level. Yeah.
Matt?
Yeah, thanks for that. Very interesting. I'm wondering, a lot of arcs are cranking in the Miocene, not just the Andes, as you know. Have you compared other arc volcanic trends? Are the Andes somewhat unique in that they peak in the Miocene versus some of the other ring of fire systems?
Yeah, globally, I would say there is a lot of other arcs. I've not compared in terms of volumes of magmatism. The APVC kind of stands out, and because it's in the right place in terms of fertilizing the equatorial Pacific, I think that's a key one. But yeah, there's going to be probably others who are affecting the global ocean chemistry. But now, whether or not they're in the right place to really make a difference, it's another question. And there is actually, I think I have, acknowledgement, sorry, just forgot that. Future NSF, I should say. Now, we have an NSF, but it's not really for this, but, as you know, you kind of divert it and do what you need to do. This is something that, this is a compilation of the relative contribution to CarbonAccumulation in percentage for, let's say, rift, volcanic arcs, mid-ocean ridges, and plumes, right? And this is just like, is to show you that in terms of how much comes out of all these settings in terms of CO2, so it's not actually helping because it's increasing CO2 in the atmosphere. The continental rifts are the most important ones, whereas the volcanic arcs are kind of down there with the mid-ocean ridges. So I will argue that this plot shows that the mid-ocean ridges, if they're slowing down, they're obviously affecting the global carbon cycle as much as the volcanic arcs fertilizing the ocean. Now, the problem there is also you have to take into account how much outgassing comes out, and when you put it together, what's the net, drawdown, because of course some of it goes into the atmosphere, and it's not helping. So, but yeah, I didn't do, I've not looked at the sort of global compilation of Miocene volcanism, to see where they are. I can't think of anything that is cranking. Maybe you guys can help me. Cranking in the Late Miocene that is in the right place.
Ian, you had a question.
Going back to Danny's point, it's probably worth pointing out that the initial cooling in the Miocene following the mid-Miocene climate optimum coincides with the first complete deep Antarctic circuit polar current. It's widely publicized that the Antarctic circuit polar current started with the opening of Drake Passage in about 34 million years. But in fact, there was an arc in the way. The ancestral South Sandwich arc was active from that time up until 12 million years ago. It was only then that you could have had a deep Antarctic circuit polar current. And that's exactly the time, about 12 million years, when that cooling starts. How that might relate to volcanism in the Andes, I have no idea. I noticed that the trend starts about that time, but I can't point to any obvious tectonic connection.
Yeah, that's a good point.
Question, yeah.
Have you thought about other sources of silica to the ocean? Because it seems like the diatoms sort of started going up around, just generally were increasing throughout the entire time period, and sort of preceded the spike in 7 million years.
You mean?
To use something like increasing grasslands or something like that.
So you're talking about?
Oh, that.
Sorry, which one? No, this one is. I'm not sure I have a silica record at all.
It was the one that had the whales in it.
Oh,
Yeah.
Yeah, diatom occurrences.
the diatom.
Increasing from around 15.
Yeah, I mean the diatoms have increased, right, throughout the Neogene. So it's not just it's when you zoom in and you look at productivity, and where is it? Here. You do see a spike in the Late Miocene. So yeah, I mean definitely diatoms have increased throughout the Neogene. So it's not just unique to the Late Miocene. Yeah. And again, there's a lot of silica going into the ocean. And if silica is the key, right, versus iron, which we don't know yet how much that is, how much the silica is playing a role versus the iron in this particular case. There's a lot of silica going into the ocean in the Neogene, from the Himalayas. I mean, we know that there's a lot of chemical weathering and physical weathering, getting stuff into the fans in the Neogene. So that's definitely playing a role. Yeah.
More questions? Barbara, you showed the increased exhumation in the eastern Andes. Do you think that can rival the Himalayas in terms of the delivery to the global ocean, or is it just not big enough?
No, the Himalayas are just like a monster, you know, those fans, and that's a different talk, but I do have a talk that is very similar where I make the case that the Himalayas are playing a key role in the late Miocene, potentially cooling. I mean, no, that talk is more like the late Miocene cooling is affecting erosion in the Himalayas, not vice versa, but who knows, maybe it's a feedback, right, relationship. There is a lot of stuff going into the fans. The amount of material in terms of mass coming out of the Andes is not even close than the one that goes into the Indus and the, you know, the big fans.
Okay, for your Zakos curve, you show a number of cooling events, like you mentioned, all throughout the Cenozoic, a number of cooling and warming. Do you think there's any other, in that history, any other pulses that could be linked to this sort of accelerated magnetism somewhere else on Earth, or
possibly
proper?
Yeah, I mean, there's I'm just looking at when for the Andes, right, the big magmatic high flux events, right, what we call them, high flux events, are about, you know, in the right time for the EOC, but would I go out and say that that's probably, I don't see the same correlations with everything else. And again, if you just look at the distribution of magmatic ages through time, that compared to the late Miocene distribution is much less, right? And as you know, there are no ashes in the foreland, that they're Oligocene in age, so yeah.
Okay, last call for Sean.
Yeah. What's the thought of the cause of your overall higher rate? Then you have that significant spike at 7.
Oh, for volcanism?
Yeah.
Yeah, that's the APVC. It's the big volcano. Oh, what's the cause of the APVC? Oh, yeah. It's is drip related. So you're dripping off a big chunk of the lithosphere over thickened crust that basically gets removed. That's kind of the, you know, the latest that I hear from my geophysics colleagues looking at the APVC. Yeah. It's a massive, though, volcanic center. Yeah.
I guess my follow-up question might be that on that rifting, the diagram of what are the global contributors to CO2, the real big change seems like dropping off of volcanic rifts is in the same kind of scale. I was curious.
Let's see. Yeah, I have a lot of extra slides in case you want. Continental rift.
Change, that's a big one.
Oh right, yeah, in the continental rifts. Yeah, that's interesting. Definitely that would probably play a big role, more than I would say at least for the Neogene, more than the mid-ocean ridges. Yeah, all these factors, obviously, all these contributes, right, the CO2, at least in the atmosphere, and so if you're slowing it down, it's going to affect the global climate. So I think that in the Earth system model, we'll have a chance to put in some additional, you know, constraints and play around with different, you know, scenarios at least. Yeah.
All right. Have a good Thanksgiving week break, and make sure to come back for the following week for several talks. And let's thank Barbara Carrapa.